Hey everybody, welcome back to HPC Tech Shorts, where every week we bring you to the water cooler here in HPC Engineering at AWS, and we introduce you to some of the topics and the engineers behind it, the people that are making the cloud a better place to do your HPC. So this week, we're going to dig into some work that we've been doing, and some of our engineers have been doing around WRF, the weather forecasting, weather simulation code. And I'm pleased to say that this week I'm joined by Matt Koop in Austin and Karthik Raman in Portland. Hey guys.
Hey, good to be here.
Thank you for coming along and sharing your home offices with us, and including your fantastic home art. Customers have been asking us for some time. Customers always ask us about how WRF in particular performs on AWS, because it's code that's usually run on large supercomputers. And so we've been doing various benchmarking efforts and testing efforts over the years to see how it performs in the cloud. More recently, of course, they've been asking us, how does it perform on AWS Graviton on our ARM-based CPU? And so you guys decided to pick that problem up and go run deep with it. And so you've got some data, and of course you published a lot of the data last week on the AWS HPC blog. But I wanted to get you here to get a bit of the backstory. So, Matt, where do we want to start?
Yeah, I think we can just sort of talk in general first, right? As you said, there's a lot of interest in Graviton2, and in particular with numerical weather forecasting, right? It's a really interesting space, and we're trying to scale up. So it looked like a really good spot where we could try out our brand new C6GN instances, which have EFA for really good performance. So where we needed to kind of start with WRF was, let's do it at a single node level. Right, so a single instance. How do we kind of make sure we're really comparing the best to the best in all cases? Because anytime you do an architecture comparison, right, there's always concern that maybe you kind of made it look better for one versus another.
Right. We use the worst compiler and the cheapest libraries on every platform except for the one that we wanted. This is in line with the "I don't believe a benchmark I didn't make up myself" theory.
Exactly. Yeah.
So we don't do that here. So, and I know you've got some data on that. So let me remember again how I can stick this up on the screen. Here we are. So
yeah.
Take it away.
So here's kind of that first level view of looking at the single instance level. And so what we did here is we took one of our Graviton2 instances, the C6GN, 16 extra large. So that's a full socket, has 64, cores there. And we compared it against, really commonly used Intel platform that our HPC customers use, which is a C5N 18X large. So it's a Skylake-based, 36 cores, physical cores spread across two sockets. And so, the first thing here was just kind of understand what is that performance on that single instance. So you can see on we have different compilers here as well. So if we're looking at the green side here on the left, we tried it with both the ARM compiler suite as well as GCC. So this is really to see, it doesn't make a whole lot of difference if we use GCC or the ARM compiler, because we've heard in the past, and we can see on the Intel side, it really does make a difference. And so what we see is there's actually very little difference between what compiler we use on the Graviton side. Now, it is worth pointing out this is a GCC 10.2, so it's a newer version of GCC. In order to get all kind of the goodness of all the N1 core optimizations, you got to use a newer version of GCC than you typically find on kind of the stock, Red Hat.
Yeah.
Yep. And so the right side there has the Intel platform. And so we use both the Intel compiler suite, which you can see in kind of the darker blue, and then GCC, again, the 10.2 version there. And you can see there is a pretty big differential there in terms of the performance. Yeah. So, oftentimes you might see, somebody trying to compare GCC to GCC, trying to make it fair. But in our case, right, we really want to choose the best to the best. Yeah. So that's why we're showing this. And so for kind of the rest of our information, it's all using the Intel compiler for the Intel side and actually just GCC for the ARM side, because it's so close and you can get that without cost. So we figured that would be most interesting for most folks.
And I think also with the MPI, you didn't use Intel MPI because you actually didn't find much in it when you did that test, right?
Right. So, yeah, exactly. So there's other parameters here too, right? The MPI, what version you're using, what distribution. So we used OpenMPI on the Graviton side, and then on the Intel side, we tried both the Intel MPI as well as OpenMPI, and we found it was really not much of a difference. So just to be easier to compare, right? We just use the same versions of OpenMPI 4.1.0 on both.
Okay, that makes sense.
And just a couple other things to note on this. Sim speed, we actually got some feedback from the blog. It was, what does that mean, right? In this case, it's how much faster is the forecast than the wall clock time, right? So a speed of 1 means I'm forecasting 1 hour and it takes me 1 hour to do the work, which, it's not really very interesting, right? So
weather forecasting is meant to be faster than real time, I heard. Matters a lot when you're talking about hurricanes as well.
Exactly. And so, this test case is called the CONUS, so it's the continental US with a 2.5 kilometer grid spacing. So it's a pretty big space. And so for one node, it's not expected you're going to get much faster than that. But so we'll see a little bit later. We scaled that up. So it's more realistic for what you might run. Other things here, you can just see the MPI tasks per node. So like many HPC codes, it can balance MPI ranks to how many OpenMP threads it does. So we're just showing, where's kind of the sweet spot. It doesn't make a whole lot of difference on the Graviton side. Intel side, right, there's a little bit highest there at sort of the 18 tasks per node, so three OpenMP ranks. But for each size as we went up, these can change. So that was just sort of the baseline to show you. Look, we're going to use the Intel compiler and the GCC compiler, respectively, for the Intel and ARM instances. And we're looking at sort of the underlying parts too that can change performance.
Right. And there's no hyperthreading on just to last bits of details. I mean, there's no hyperthreading on a C6GN on a Graviton instance. We've turned off hyperthreading on the Intel instances, so there is 36 real physical cores, right?
Yeah, exactly. It's a good point. Okay. And sort of the headline here is if you look at these numbers, right? These are kind of absolute across them. So you can see, the Graviton side is 1.079, right? And the Intel side there is 1.14-ish at the highest. Right? So that's pretty good comparison there on an instance to instance level, and that was actually a little surprising for us, to be honest. So if you kind of scroll down a bit, one of the characteristics often of numerical forecasting codes is that they're known to be kind of memory bandwidth intensive. And so, on the, I've helpfully confused you probably by putting these on the opposite sides here. But the ARM processor on the right side there, exactly, is one socket and it has 8 memory channels. So we've got 8 memory channels feeding into 64 cores. The Intel side, which it's on the left now, has 2 sockets, and each of those have 6 channels. So, if we're looking at kind of memory bandwidth, the the Intel side actually has 12 channels versus the 8 channels on kind of an instance level. And so that was kind of interesting, when we first looked at this data to say, wow, that's kind of surprising that the Graviton instance was doing so well, even at just the single instance level. So, we kind of, yeah.
That's quite. I mean, it's kind of a shocking result at first, because I mean, well, to begin with, we kind of assumed actually that weather code. I mean, we've always been sort of force-fed this dictum that weather codes are network latency sensitive, and we'll get to that in a minute when we talk about EFA, but also CPU intensive, right? And and they may be CPU intensive, but there's obviously something else going on here around the memory bandwidth, obviously.
Yeah. So I think that's where the bandwidth efficiency story comes into play. So I think if you scroll down further, if you'll see that. So as Matt pointed out, right, based on the number of memory channels, so although the absolute memory bandwidth is slightly better on Skylake due to like 1.5x more memory channels, that is 12 versus 8, the Graviton2 has a higher memory bandwidth efficiency. That means it can achieve higher percentage of the peak. So for numerical weather prediction codes like WRF, which are known to be memory bandwidth bound at a single instance level, this actually bridges the gap further. So that's why the Graviton2 instances are actually able to match more closely to the performance of a 12-channel Skylake-based instance. So in the graph that you see here, the left side, the blue bar is showing the C5N18X large memory bandwidth efficiency as measured by the de facto industry standard stream triad benchmark, right? And the orange bar is the C6G and C6GN bandwidth efficiencies, so which are much more higher compared to the C5N.
Right. And that's, I mean, is there an architectural difference here that do we expect this?
This was, I think, more to do with the fact that on an Intel-based instance, as Matt earlier pointed out, you have dual sockets, right? So there is an additional thing of going through the UPI links, right? When you have to make use of the whole memory bandwidth across all the 12 channels. That's not there. So yeah, I mean, it was QPI in the earlier generation. With Skylake, it is UPI, the ultrapath interconnect. But on Graviton, you do not have that penalty of going through another socket to invalidate anything, especially when you want to achieve higher memory bandwidth.
And I mean, there could be. I mean, that two-socket aspect could also be feeding into things like, the EFA device obviously is only connected to one of the sockets. It's on a PCI bus on one of the sockets. It's not connected to both sockets, so the QPI becomes even more important again. I mean, it seems like the good old days of just having one CPU in a box is kind of actually good. It seems like it's good for WRF.
Yeah, it does. I mean, we spoke about single instance here, right? So I think even the multi-instance performance is like a good segue to talk about that.
Yeah, right.
The multi-instance performance actually shows that clearly, right? So in terms of the MPI communication, so WRF uses a 2D grid decomposition, which is over the simulated region, and we call that a domain, right? So a portion of the domain is decomposed into individual MPI processes. So when the patch and that portion of the domain which gets decomposed into individual processes, that's called a patch. So when the patch gets smaller, the ratio of the perimeter points to the interior point increases, and that's what basically translates to the communication to compute ratio. So one of the key things to hide the communication is that is standardly used in a lot of HPC applications is hybrid MPI OpenMP parallelism, right? So you have distributed parallelism and you have shared memory within the node. So we make definitely use of that because WRF has the capability to run both MPI and OpenMP. And as Matt earlier pointed out, we ensure that for every point in the node or every point in our scaling chart, we are using the best MPI and OpenMP that's possible within the node. So if you look at the graph here, on the left chart, this is the performance on per instance basis. And on the x-axis is the number of instances, and the y-axis is the simulation speed. So as you see, that the scaling is pretty good on the C6GN and the C5N instances, which have EFA and 100 gig of network.
Yeah, there's like daylight if you're not using EFA, and which is what that like. Where's my highlighter thing? This line here, that one there. That's the non-EFA line.
That's correct. Mm-hmm.
That's like, and for the sake of everybody watching at home, that's realistically that's TCP is our MPI transport, which is pretty awful. And so that's actually not too shocking that it performs badly, but.
Right.
Okay, but the other two lines are like overlapping, Karthik. I mean you don't get much better fit than that.
Right. So in terms of paddle efficiency, so that speaks about the paddle efficiency. So if you scroll down a bit, the graph actually talks about the paddle efficiency across the different instance types, and here we see that the C6GN, which is represented in orange here, has about a 90% of paddle efficiency at 112 nodes, which is pretty awesome for WRF. And C5N is around 85% here. So EFA really helps in scaling. And we do see that in these numbers.
This seems like what you need is a box with a CPU in it, a whole bunch of memory, and a good network adapter. And the more memory channels or maybe the more CPUs that you put in there actually seems to detract or maybe just overcomplicates things. I mean, it doesn't seem like it's adding anything to the performance for this code. It's an astonishing outcome.
For typically memory bandwidth bound applications, it's pretty common we see that, but it was pretty impressive that we could get this result on Graviton. There's another component which we didn't touch upon in the previous graph, and maybe that was another set of questions that we got from a lot of our readers. So if you go back up in the earlier on the right side of the chart, so this is the performance on a per core basis, right? So here the x-axis is the number of cores, and again the y-axis is the simulation speed, and higher is better. So someone would ask and say that, hey, on a per core basis, C5N is better. Why is that? And this is where the number of cores per instance comes into play, right? So if you look at a point, so say if we look at the 2000 core point in this graph, what that means is that when you're running at 2000 cores, the number of cores that you have, the number of instances that you need on a C5N is significantly higher than what you need on a C6G or a C6GN, because C6GN has only 64 cores per instance, and C5N has 36 cores. So this is an expected behavior because you are essentially getting higher overall memory bandwidth when you are able to run on more number of instances. So that's like a clarification for a lot of our readers who look at these performance on a per core basis.
Okay, that's interesting. And so it is, again, it just keeps coming back to memory bandwidth. That's
correct.
All right. Now, so we've so that's actually kind of pleasing from an EFA point of view. And I think if folks watched last week, and I'll put a link to it in the show notes, we had a discussion with Brian Barrett, the principal engineer for Elastic Fabric Adapter, and we're talking about how shocked we were, and more to the point, how shocked I was when we actually did really good stuff with weather codes with EFA, because we didn't design EFA to be a super low latency, single packet MPI ping pong champion. And Matt, I think I even remember having some discussions with you about it before it launched, and we were a bit ambivalent as to whether this thing was really going to work and really nail it for a bunch of latency sensitive codes. But it turns out not so much, right?
Yeah. No, it works quite well across a large number of apps. So
yeah. So I get Karthik, where I think you wanted to, and we've got time. We've definitely got time to talk about. I think your favorite topic, collectives, and how they're involved here.
Yeah.
Where do we want to go?
So we wanted to deep dive a bit and try to look at what kind of communication MPI routines are actually used for this particular case that we ran on WRF, right? So this basically shows the amount of time that is spent on each of the routine, and all of them are run with 96 nodes for the respective instances. And so this one basically shows C6GN, 16x large at 96 nodes, and this has EFA. And you can see that the majority of the time spent is in MPI broadcast. And most of the other routines are also collective routines, like the scatter V, gather V. And it does show that in spite of it using collectives, and we actually have drilled down a little bit on the message sizes as well. And these are actually pretty small in the 4 to 8 byte range. That's not there in these.
It's not there. Okay, right.
Yeah. But what we are trying to show here is that in spite of it being dominated by collectives, the performance is pretty good, and the parallel efficiency that we are able to achieve at 90% is possible primarily because of EFA, right? If you compare that to the TCP, if you look at the MPI broadcast time is significantly higher, and some of the collective times like gather V starts increasing. And it also matters on how many ranks and threads that you're using on a per instance basis.
Okay. It's good because you guys did as Matt explained earlier, you did the comparison with Intel MPI, and you made sure that, as a baseline, there was no difference. There wasn't enough difference to talk about. So we stuck with Open MPI. Talking to Brian last week, he thinks that collectives is really the place where there's the most low-hanging fruit for us to improve. So this, in terms of the libfabric and Open MPI interface. So that actually tells me that we could come back here and look at this in 6 months' time, after we've hired enough programmers to apply to that particular collective challenge that we want to pick off. We could come back here in 6 months' time and see even better performance. It's quite possible.
yeah, across both of them, right? I think that's the value.
Yeah, that's true. All right, this is really interesting. It's interesting when we did the last couple of putts that we've done where we've compared a code like GROMACS or OpenFOAM on across both x86 and Graviton. The answer that we've come out has been, if you want the answer absolutely faster wall clock time, pick Intel. Pick the Intel platform. Go for a C5N. If you absolutely want, if you want the result soon, but you're price sensitive and you've got the time to be able to trade off to get a cheaper answer, absolutely go for Graviton, right? Now, and the 40% price difference between the two is kind of, that's pretty makes people pretty happy when they can do the Graviton version of that. This is one of those scenarios where there is nothing in it in terms of per node performance, and it's just straight up going to be 40% cheaper.
Yeah, I think in this one it ends up, when you're looking at sort of the highest end case, 112, I think it's about 30% cheaper overall, but absolutely, yeah, we don't see the sort of trade-off that we often see in other cases. So, and if you actually scroll down a little bit, we had another. I just popped in another chart that we had in the blog, which we don't normally see these sorts of things elsewhere, but this is the plotting of sort of the cost for the compute time versus how much speed. So the speed, all the way to the right, you kind of choose how fast you want to go. So in this case, the 112 is, it's scaling pretty well. So it's almost 1-to-1 mapping. So, I want to do 100 times faster than real time, right? I can look look and see, well, which one is the cheapest one, right? So, we can see it. If you want to go the fastest, right, the answer is, yeah, you should pick an instance with EFA, and it's going to be the cheapest, right? If you really want to go kind of slow, right, like you want to forecast only an hour in an hour's time, right? Then you would choose, in this case, look, the orange line, which is the C6G, right? Because you're really not gonna need the EFA performance. So.
Just to be clear, we don't recommend this, folks. If you're watching at home, please don't do this, kids.
Yeah, but having said that, I think a lot of research cases might fall into that category, right? I mean, if you are just wanting to see, say, how my code really works, and if you really are not really doing the actual prediction, some of the customers are indeed okay to use the C6G instances as well for that. So.
Just going to put the address to the HPC blog on the screen. If folks want to actually read the full write-up that you guys provided on the HPC blog, this is the place to go. They can get all of the details. And in fact, there's a bit more. There's another blog post there coming this week related to some work that NOAA's been doing for training their forecasters using cloud stuff. So I feel like it's weather week here at Tech Shorts. And that's not just because I live in London, where we have weather a lot. But gentlemen, thanks for coming along today. I think this is a really interesting topic. I want to come back in 6 months' time and see if those collective operations have actually moved the needle again in WRF. So we should get into that.
Yeah, I'd like to just add that it was really good collaborating with NCAR for some of the test cases that we were able to provide. So I guess in the blog we mentioned about the V4 version of WRF, and there is no open source test cases that were available. So as part of this effort, we were able to collaborate with NCAR and make those cases available publicly, so anyone can use them and try out and try to reproduce results that we have.
Oh, great. And where do we make them available? Are they on NCAR's site or are they on our site?
They are on NCAR site, yes. They are on NCAR site, and it's actually referenced in the blog.
All right. Well, look, thanks for coming along. And I guess to everybody else at home, if you're watching and there's any other topics that you want to see us cover, find us on Twitter. Our DMs are open. You can give us some guidance on what you'd like to see and hear on future shows. But until the next show, I guess thanks very much. Thanks, Matt. Thanks, Karthik.
Thanks.
Thank you. Thanks for having us.
Have a great one.